there was this guy named Coulomb, and he discovered a law. And it was a big deal. So they named the law after him, and they named the measurement of charge after him, the Coulomb. So we're going to talk about that. We're going to talk about his law, what it means. And so let's begin. We have this thing called charge. Okay, and what do we mean when we say something has charge? Well, okay, there's what we mean by it today, which is, but there's what they meant by charge a long time ago when they created the word charge. And here's what they discovered, that, and we discovered that if you, rub certain objects together, they'll pick up a charge. Like, we rubbed plastic with hair. If you rub any kind of plastic with hair, the plastic picks up the electrons off your hair, and thus it applies. It applies forces to other objects that have been rubbed in the same way. And what we've discovered is there's two kinds of it. And so what Benjamin Franklin thought was that if you rubbed certain objects together, some objects would collect more electrical fluid than the other, and thus would have a surplus of charge, and he called that surplus positive charge. And then you took the charge away from something else, so it would have a lack of electrical charge, and so it would be negatively charged. And of course, the lack of electric fluid the surplus wants to get back to the debt, okay? And so they draw each other together. This is what Benjamin Franklin thought. And it kind of made sense in his time. And then, of course, if you have a positively charged object and another positively charged object, they push each other away. They repel. And if we had an object where I had I had negative charge and negative charge over here, what Ben Franklin thought was a lack of electrical fluid, they would push each other away as well. So, and these represent forces, electrical forces. I'll call it F sub E for electrical force. And this was the best understanding for good 150, almost 200 years. Because they didn't know that matter was made out of atoms, and they didn't know that atoms were composed of electrons, neutrons, and protons. But that's okay. They went a long way with just this idea. And so they said what they meant by charge was a surplus or a deficit of this fluid that would apply forces to other objects, and they call that being charged. That's what they meant by being charged. Now, we know today that really, if something is negatively charged, it has more electrons than it has protons. And that if something has positive charge, it's because it has more protons than it has electrons. That there are two particles that we're made out of. Everything around us, all the matter that we see and feel, is made out of atoms, and atoms have these constituent parts, electrons and protons. And that it is the electron that carries the negative charge, and it's the proton that carries the positive charge. But again, they didn't know that until, roughly, about a little more than 100 years ago. They did experiments that showed what the atoms are made out of. Now, they had a way for, they needed a way for measuring the amount of charge. And they had a way of doing it. It involved current, and current is the flow of charge. And they defined this thing called the volt, which we haven't talked about yet. And so if you have a certain voltage, could you guys please settle down? I am recording this. All right. If you have a certain amount of voltage and you have a certain resistance, you get a certain amount of current, and they said that the amount of charge that flows in 1 second, if you have 1 amp, they called that one Coulomb of charge. So they defined the Coulomb of charge based on current, but we're not going to worry about that. We're just going to say that a Coulomb of charge, 1 Coulomb of charge is just, think of it as just being a big basket of charge. Like, we'll say here's 1 Coulomb. It's a lot. It's actually a lot of charge. So just think of it as kind of being like a container that has a certain amount of charge in it. It's 1 Coulomb. It's a quantity of charge. Now it turns out that a proton has the smallest amount of positive charge you can get out of ordinary matter. Okay, a single proton. And a single proton, which I'll P plus, has a charge of 1.6 times 10 to the negative 19 coulombs. That's a very, very tiny amount of charge. 10 to the negative 19. I don't even know what that is. And an electron just has the same amount of charge, but we say it's negative. And it's very convenient to call protons, give protons what we call a positive charge, and electrons a negative charge. It matches how Benjamin Franklin described it, and it works mathematically as well with Coulomb's law, as we're going to see. So just think of it as a whole lot of protons. Well, let's figure out how many protons does it take to have a Coulomb of charge. Well, all you have to do is reciprocate this. If you say 1 proton has 1.6 times 10 to the negative 19 Coulomb, what am I doing? Coulombs per proton, okay, you get, when you punch that into your calculator, you get 6.25 times 10 to the 18 protons. Now, 10 to the 18, that's 10 to the 9 times 10 to the 9. 10 to the 9 is a billion. So it's a little more than 6 billion protons makes 1 Coulomb of charge. So 1 Coulomb is kind of a lot. Well, it's certainly a lot of protons. And, of course, 1 Coulomb of negative charge, negative 1 coulombs, is 6.25 times 10 to the 18 electrons. So you can use it with either protons or electrons. So it's a lot of charge. Now, a Coulomb, so let's say I've got like a certain quantity of charge. Let's say I got a whole bunch of charge here. Let's say I have got 3 coulombs. Okay, well, you would say 3C. This is how you abbreviate. A Coulomb is a capital C. And what's the variable I use to represent charge? Well, like we use F for force, V for velocity, A for acceleration. You'd think we'd use C for charge, but we don't. We use the letter Q. So you would say Q is equal to 3 coulombs. So when you see a Q, sometimes they use capital Q, In the book, sometimes they'll use lowercase q, but q, usually lowercase, means charge. Now, we just used the letter q for heat, didn't we, in chapter 12? Sorry, you have to know the context. We have more quantities than we have letters. All right. Now, let me tell you something. If I were to rub a balloon on my head, I would deposit a negative charge on the balloon, like this. So let's draw a balloon. And let's say I put some charge on there, some negative charge. Now, here's the thing. If I put 3 coulombs of negative charge on a balloon, this would be a very bad day if you were anywhere near this balloon. You would probably be killed, because there would be gigantic lightning bolts coming off of this balloon. This is so much charge that it's really far beyond what we would ever experience with any kind of static electric experiment. In fact, with static electricity, you're usually dealing with millionths of a coulomb. So you would say a charge might be 3 millionths of a coulomb. Well, this is awkward. So usually we use scientific notation, and you say, well, that's 3, what is a millionth? 10 to the negative 6. That's a millionth of a coulomb. Well, we're going to get even lazier here. Times 10 to the 6, that's a lot to write down. So this is what we usually do, and this is the quantity of charge we deal with usually in static electrical situations. We would say 3 microcoulombs. This is a mu. Now, what did we use mu for in the first semester? Coefficient of friction. But now we're going to use it as a metric prefix. It is one of the metric prefixes. And if you see this micro in front of a unit, or mu, see, this means microcoulombs, or times 10 to the negative 6 coulombs. The word micro in science means times 10 to the negative 6. Micrometers. Micro, and they abbreviate micro with the mu. I don't know why they don't use millionth. They don't. They use micro instead of millionth. But micro and millionth is the same thing. Just the way, that's the language we use in science. Yes, it's kind of annoying, but. So this is more typical of what you're going to see. And when you're doing calculations, what you have to remember to do, when you see that 3 microcoulombs, when you type it into your calculator, you would have to do this. You would have to say 3 microcoulombs. You would go 3 times 10, or e to the negative 6. Okay, you would need to, if you see that micro, to put that negative 6 in there. Otherwise, your answer is going to be it's going to be 1,000,000 times too big. So this is a unit of charge. Okay, so this guy named Coulomb started doing experiments with charge, and he empirically derived an expression that describes the force that these charges apply to each other. And that's what we're going to show right here. Suppose I put some positive charge right here, and I'm going to call that Q1. And I'm going to put some positive charge right here. Could be a different amount. Call that Q2. And what are these charges going to do? They're going to push away from each other. with equal and opposite forces. So we're going to say this is the force of charge 1 on charge 2. This is the force of charge 2 on charge 1. And these forces will be equal in magnitude but opposite in direction. Newton's third law says that has to happen. Remember, for every force on one object, there must be an equal but opposite force on another object. Always. And then these two objects have a certain distance between them. I'm going to call it R. Your textbook uses the letter D, but I'm going to use the letter R. And so Coulomb started doing experiments. And what he started doing was he would measure the charges, measure the distance between them, and measure the forces that were exerted, and find a mathematical relationship that describes how these quantities interact. And this is what he found out. Well, the force, the magnitude of the force of 2 on 1 or 1 on 2 is equal to this. Well, first, if I make Q1 bigger, the force does get bigger. And in fact, it gets bigger, it's directly proportional to. That is, if I double Q1, I'll double the force. If I triple Q1, I'll triple the force. The more force I have here, proportionally, the more force I've got. So it's directly proportional to Q1. Now, by the same logic, it's directly proportional to Q2 as well. And then, wouldn't you expect the force to get weaker if the charges are further apart? That sort of makes sense, doesn't it? The farther apart the objects are, the weaker the repulsive force. You bring them closer together, the force gets stronger. So it's inversely proportional to R, where R is the distance apart. But not just R squared. That is, he noticed that if he doubled the distance between the two charges, the force was only 1/4 as big. If he made the distance, 1, 2, 3 times farther away, the force is only 1/9 as big. So the force decreased by the square of the distance. Now gravity does the same thing. Remember the Newton's law of gravity, decreased by the square of the distance. Decreasing by the square of the distance is a property of three-dimensional space. Anything that spreads out in three-dimensional space gets weaker and weaker and weaker, right? By the square of the distance, because you're spreading out over 3 dimensions. You get weaker by the square of the distance. That's a property of three-dimensional space. And this is all you can do. You can only vary the value of the charge, and you can only vary this, and that will get me a different force by these relationships here. But look, let's take a look at units here. This is measured in coulombs. Q1 is in coulombs, Q2 is in coulombs. So you got coulombs times coulombs. What is that? And this is measured in meters. So R squared is meter squared, right? And of course we know that force is measured in newtons. Now does a newton equal a coulomb squared per meter squared? No. There is a constant of nature that I need to solve for here to make the units work. And to tell us how strong the force is actually going to be if I use coulombs and meters. We need a constant of nature to make it all work out. And we use a lowercase k right out in front there. This is called the electric constant. Now Coulomb did the experiment and he solved for K. I mean, it's pretty easy to figure out what K is if you have the right equipment. You just take this equation and you solve. K, our electric constant, will be equal to the force that I measure between the two charges times the distance between them squared divided by the charges. And when you do the experiment and you plug in the values, you get a number. You get a value for K. And that value turns out to be 8.99. Or you can just use 9 if you want. Round it off to 9. 8.99 times 10 to the 9, positive 9, Newton meter squared per Coulomb squared. Look at those units. Force is measured in newtons. R squared is meter squared. Q times Q is Coulomb squared. And this is the electric constant. This is a property of our universe. This tells us how strong the electric force is. And it turns out to be really strong. I'll tell you how strong it is in a little bit, but it's amazingly strong. Last thing. So now we know the value of K, the electric constant. But there's one more thing that I'm going to show you, and this is a little bit advanced for this class, but because we haven't talked about unit vectors that much. I think, well, maybe I did with gravitation. But these charges push each other away. And we need a way of saying the direction of the force is away from the charges, directly away. They push each other in opposite directions from each other. They just go, boom. And we have a name for it, and it's kind of weird. It's R hat. That's how we say it. R hat. Now this R is not this R. This R, the distance between the charges. It has nothing to do with that. It's simply a shortcut way of saying away or repel. They repel each other. Does repel have one or two L's? One L? Doggone it. Okay. So if you say R hat, that means it's the two charges are repelling each other. Okay? And this right here, F equals K Q1 Q2 over R squared in the R hat direction. This is a direction. That means away from direction. This is Coulomb's law. And we can do, you're basically in the homework, you are going to use this to solve problems. So let's do that. Let's work an example problem. Is this right? Yes, honey. Okay. Someone tell Laura Greider she needs to go to the office. Okay, so let's work this example. Here's what we're given. Suppose I've got a charge, Q1. And I'm going to say that it's equal to 2 microcoulombs. Again, what does that micro mean? 10 to the negative 6. And then over here, I'm going to put Q2, and it's equal to negative 3 microcoulombs. Now, what are these? These are opposite charges, so what are they going to do? They're going to attract each other. And we want to find, one other thing. The distance between them equals 0.50 meters. So 50 centimeters apart. I want you to find the force, the electric force between them, using Coulomb's law. Now, if you're watching this on the video, pause the video right now and work it yourself. Okay. So let's solve it. Well, here's Coulomb's law. And now all we need to do is plug in the values that we know. There's K. And then there's Q1 is 2 microcoulombs. And Q2 is negative 3 microcoulombs. And I'm going to divide it by 0.50 meters squared. And that's going to be in the r hat direction. So let's do that. Let's see. So 8.99 times 10 to the 9 times 2. Now what do I have to remember to do to this 2? 2. That's right. Negative 6 times negative 3 to the negative 6. Then I'm going to divide that by 0.5 squared. And I get negative 0.2156. See that? So negative 0.21, and I'll round it off to 216 newtons in the r hat direction. Now I'm going to do something a little different here. And this is the way I like to do it. You could write this as your answer, and that would be correct. I like to do it like this. I like to put that negative in here with the unit vector r hat, because what does it mean? What does that negative mean? Anybody? They're attractive. So if I define r hat to be repulsive, negative r hat is the opposite direction of that, which means it's attractive. They're trying to pull together. And this is why we kept Benjamin Franklin's positive and negative convention. Even though he was wrong about what was actually happening, he thought that there was this electrical fluid that was being exchanged. And it's not. It's just that there are particles called electrons and protons, and if you have more or less than themselves, you've got a charge. But it still works, because notice that this was a positive charge and this was a negative charge. That gave me a negative answer. That means that it's attractive. I mean, what would happen if they were both negative? If this was -2 and this was -3, what's a negative times a negative? Positive, so they're going to repel. That makes sense? Okay, so you're going to get problems, in the book where you're going to use Gauss or Coulomb's law, and where you're going to have to solve. Maybe you'll get a problem where they give you everything except Q1. You'll have to solve for Q1. Or they'll give you everything except R, and you'll have to solve this for R. But you're just using this mathematical model here that describes how electrical particles behave in terms of force to solve problems. Now, the last thing I want to show you. Let's compare gravity and electrical force. So gravitational force has this equation. The gravitational force is equal to big G times m1, m2 over r squared in the negative r hat direction. The electric force is equal to K times Q1, Q2 over r squared in the r hat direction. Now, do you see that these two equations look very similar to each other, don't they? This gravity is an attractive force. That's why we have the negative with the r hat. Massive objects always attract. Now, gravity is different than electric force in that gravity is always attractive. There's no such thing as negative mass. Any massive object has a positive mass, and thus all positively, all massive objects attract other massive objects. But with electric force, we have two kinds of charge. We have charge that like charges will repel, unlike charges will attract. So you got two kinds. You have attractive force and repulsion. Here it's just attractive. Here it can be attractive or repulsive. But notice that both of them have this r squared. That is, gravity spreads out in three-dimensional space, just the same way that the electric force spreads out in three-dimensional space. Anything that spreads out in three-dimensional space, light, sound, gravity, electric force, decreases by the square of the distance. Now let's take a look at one other comparison. Let's take a look at big G. 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And we're going to compare that to K, which is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Now, how a kilogram compares to a Coulomb, they're totally different things, and how big a Coulomb is arbitrary compared to how big a kilogram is. But I think you can still see something here. Gravity is an incredibly weak force compared to the electric force. You're sitting next to somebody right now. You both have mass. Are you feeling gravitational attraction? No. You might feel something else, but it's not gravity. Okay? Now, do you feel an electrical force, an electrical repulsion, or an electrical attraction? No, you don't right now. Why is that? It's because you don't have a net, you have a net mass, but you don't have a net charge. Your body is made out of almost exactly, to like a zillion decimal places, you have the same number of protons as you have electrons. They exactly balance out, and they're all distributed throughout your whole body. And so, you don't have a net charge, and thus there's no net electrical force. Okay, but let's take two people here, and let's see what happens. Suppose I took Ikra. She's wearing a hat. Okay, and Lauren. And let's say I have Harry Potter powers, okay? I have this magic wand, and I will, just by magic, deposit 1%, just 1% more electrons onto each of them than they have to begin with. That means that for every 100 electrons they already have, I'm just going to give them one additional electron. Just one out of 100. That doesn't seem like very much. So now Ikra and Lauren have this negative charge. Now what? So they're going to feel a repulsive electric force, right? Now how much? Just adding 1% more electrons. What do you think this force is going to be? Is it going to be a lot? Oh, it's going to be a lot. It's going to be so much repulsive force that, in fact, if I could do this, it would be a very bad day for you and for everyone in Clovis. The repulsive force that they would experience would be on the order of magnitude of 10 to the 25 newtons. Now, what is that? That's equivalent to the weight of the Earth, which is kind of ridiculous. Just 1% more electrons, if they're standing right next to each other, gives 10 to the 25 newtons. Now, what would happen? Okay, first of all, you wouldn't feel a thing. Don't worry. It would be totally painless because every atom in your body would be obliterated before any pain signals could get to your brain. You would vaporize. You would crush the air in front of you and compress it so quickly that it would give off a huge amount of energy. And in fact, if this is Buchanan High School right here, and maybe here's the Energy Academy building right here, you would see it would be like a thermonuclear explosion. In fact, it might be, considered one of the greatest explosions in the history of the Earth. And so, what I'm saying is that I can't do that. When you have static electric cling, when you pull your socks out of the dryer and they want to stick together, the amount of charge there is tiny compared to the amount of charge in the matter itself. You don't need very much more charge, though, to get a significant force. The electric force is incredibly strong, much stronger than gravity. In order to feel your weight, the weight that you feel right now, you need a whole planet of mass under your feet. There's a whole planet underneath your feet right now, the Earth. It's 5.98 times 10 to the 24 kilograms of mass right below your feet. That's how much mass you need to feel pretty good gravity. This is nothing. I mean, gravity is nothing compared to this. Now, here's another fun thing that you can show using Coulomb's law. Here's the Earth. Here's a little mushroom cloud coming up, from our first experiment. But here's a North Pole and a South Pole. All the penguins are down here, by the way. No penguins up here. If I were to take an M&M, plain, not peanut, and I were to remove all of the electrons out of the M&M and put them in a little electron box, and I were to put that little electron box, not drawn to scale here, people, at the South Pole, and I were to put the M&M, now all it has is protons and neutrons, right? It has no electrons. So this has a net positive charge, and this has a net negative charge, but one's on the North Pole and one's on the South Pole. What do you think there's going to be an attractive force here? Okay, the attractive force is equivalent to the weight of an SUV. Thousands and thousands of pounds of force. Tens of thousands of newtons of force. Separated by 9,000 miles. I'm sorry, 13,000 kilometers. Okay, this is for our European students. All right. That's insane. And it is insane. You could never do this. You can never separate all the electrons out of an M&M from all the protons that are in that M&M. Just can't. Won't work. So the electric force is really, really strong. Now, you are made out of atoms. You, me, the floor, everything, all the ordinary matter that we interact with is made out of atoms. And an atom has a nucleus. Now let's say the nucleus were about this big. If the nucleus were about this big, the electrons would be over by Alta Sierra. Now I can't draw that under the document camera here. So I'm just going to pretend like here's the electron cloud, right? So here are all the protons and neutrons. And here's the electrons. And they're spinning around like this. What's in between them? Empty space. Atoms are 99.9999999% empty space. Therefore, you are 99.999999999% empty space. We're ghosts. So how come if we're ghosts, how come we can't walk through walls? Okay, I'll tell you why. Let's say that Ryan says something offensive and gets his face slapped again. So here's an atom on the surface of his face. Okay, here comes her hand. Well, yeah, assuming. Now, what happens here is that, you would think if it was mostly empty space, the hand and the face would just pass right through each other without touching. Because there's so much empty space, the odds of any atoms actually hitting, the nuclei of the atoms actually hitting are practically zero. You should be able to just walk through walls. Or the gravity should just pull you down through the center, into the center of the earth. How come it doesn't happen? Because this electron is buzzing around and it creates like this cloud of charge. And what happens is that the cloud of charge of this atom over here gets really close to the cloud of negative, and this is a negatively charged cloud. And it gets close to this negatively charged cloud. And they get close enough that the repulsion between the electrons pushes the objects apart. So when my hands clap together, the electron clouds here that are negatively charged are interacting with the electron clouds here that are negatively charged, and it's that repulsive force between electrons that keeps my hands from just going whoop. Okay? So that's what's going on. This is how matter interacts. When you're in contact with something, it's the electron clouds of your atoms, the negative repulsive force that keeps things from moving through each other. Okay? I'm sorry? Well, if you could slow down the electrons, could you walk through walls? No, you can't. And that's a quantum mechanical thing. The rules of physics that describe how these electrons behave and these protons behave is called quantum mechanics. And we don't go into that in here, but it's really wonderful and amazing and truly weird physics. And it works. It works exactly right. It's the best model of nature we have. Quantum mechanics is the weirdest science, and it's the most accurate science we have. Study it someday. But you'll have to go to college to study quantum mechanics. Okay, so again, you're just going to be doing mainly problems like this and answering questions about using Coulomb's law. So good luck with that. That is all.